Imagine being dropped into the coldest, darkest place you can possibly imagine. There is no air to breathe, no sunlight to warm you, and no rescue coming. Every machine we've ever built eventually wears out, freezes, or simply stops working. Yet there is one extraordinary exception. More than 24 billion kilometers away from Earth, a small spacecraft no larger than a family car is still alive. It was launched in 1977, when cassette tapes were cutting-edge technology. Computers had less power than today's smartphones, and no one expected it to survive beyond a few years. Yet nearly half a century later, Voyager 1 is still talking to Earth. Every signal it sends has traveled for almost an entire day before reaching NASA's antennas. Every command engineers send takes nearly another day to arrive. Despite being farther away than any human-made object has ever traveled, Voyager continues to send back priceless scientific discoveries from a region no spacecraft had ever explored before. But this raises an incredible question. Deep space is unimaginably cold. Temperatures hover just a few degrees above absolute zero, the coldest temperature physically possible. Electronics usually fail under extreme conditions. Batteries die. Metals become brittle. Machines stop working. So why hasn't Voyager frozen? What secret allows a spacecraft built almost 50 years ago to survive where almost nothing else could? Is it simply luck, brilliant engineering, or something far more remarkable? Today, we're uncovering the incredible story behind one of humanity's greatest engineering achievements, and revealing why Voyager 1 continues to defy expectations nearly 50 years after leaving Earth. To understand why Voyager is still alive today, we first need to go back to the early 1970s. NASA wasn't trying to build a spacecraft that would last half a century. In fact, Voyager was designed for a much shorter mission. Its primary goal was to take advantage of one of the rarest events in our solar system, a planetary alignment that occurs only about once every 176 years. For a brief window of time, Jupiter, Saturn, Uranus, and Neptune lined up in a way that allowed a single spacecraft to visit multiple planets using gravity assist. Instead of carrying enormous amounts of fuel, Voyager could steal a tiny fraction of each planet's orbital energy, slingshotting itself toward the next destination. It was an opportunity no space agency wanted to miss. On September 5, 1977, Voyager 1 lifted off from Cape Canaveral. Despite its name, it actually launched after Voyager 2, but followed a faster trajectory that allowed it to reach Jupiter first. The mission quickly became one of NASA's greatest successes. Voyager revealed active volcanoes erupting on Jupiter's moon Io, the first volcanoes ever discovered beyond Earth. It exposed Europa's cracked icy surface, hinting at a hidden ocean beneath. Then, during its breathtaking flyby of Saturn, Voyager captured stunning images of the planet's rings and its mysterious moon Titan. But Titan presented NASA with a difficult choice. Scientists wanted a close encounter with the moon, believing it could reveal clues about the early Earth. Achieving that flyby required changing Voyager's path forever. Instead of continuing toward Uranus and Neptune like its twin spacecraft, Voyager 1 would be redirected upward, leaving the plane of the solar system entirely. Its planetary mission ended in 1980. Most spacecraft would have been retired. Instead, Voyager 1 began a journey no spacecraft had ever attempted before, a voyage into the unknown between the stars. And that was where the real challenge truly began. People often imagine space as being empty and peaceful. In reality, deep space is one of the most hostile environments imaginable. As Voyager traveled farther from the sun, sunlight became weaker and weaker. Near Earth, sunlight provides enough energy to power satellites with solar panels. By the time Voyager reached Saturn, sunlight had already become about 100 times weaker than it is near Earth. Beyond that, solar power was no longer practical. Then came the cold. Interstellar space is only a few degrees above absolute zero, the lowest temperature the laws of physics allow. At these temperatures, almost every source of external heat disappears. But freezing isn't Voyager's only problem. Invisible cosmic rays constantly bombard the spacecraft, carrying enormous amounts of energy capable of damaging delicate electronics. Tiny particles of dust, traveling at tens of thousands of kilometers per hour, can strike like microscopic bullets. The vacuum of space slowly pulls heat away through radiation, while decades of continuous exposure gradually age every wire, computer chip, and mechanical component on board. Even communication becomes an enormous challenge. The farther Voyager travels, the weaker its radio signal becomes. By the time that signal reaches Earth, it's weaker than the energy produced when a snowflake lands on the ground. Engineers have to detect that whisper from billions of kilometers away. Every year that passes, Voyager drifts farther into an environment where almost everything is working against its survival. The odds seem impossible. A spacecraft built in the 1970s shouldn't still be functioning under these conditions. And yet, it is. Which brings us back to the question that has puzzled millions of people. If deep space is so unimaginably cold, why hasn't Voyager frozen solid? The answer lies inside the spacecraft itself. The biggest misconception about space is that it's cold in the same way a freezer is cold. It isn't. On Earth, your body loses heat because cold air or water touches you and carries that heat away. That's called conduction or convection. But in the vacuum of space, there is almost nothing touching Voyager. There is no freezing wind, no icy air, and no atmosphere to rapidly drain away its warmth. Instead, Voyager loses heat much more slowly by radiating it into space. That difference changes everything. When NASA designed Voyager, engineers knew sunlight would eventually become too weak to power the spacecraft. Solar panels were never an option for a mission heading toward the outer solar system. Instead, they gave Voyager its own miniature power plant. Mounted on a long boom extending from the spacecraft is a radioisotope thermoelectric generator, or RTG. Inside it is plutonium-238, a radioactive material that naturally releases heat as it slowly decays. Unlike a nuclear reactor, there's no chain reaction and no moving parts. The plutonium simply produces a steady flow of heat, day after day, year after year. Special thermoelectric devices convert part of that heat directly into electricity, powering Voyager's computers, instruments, communication systems, and onboard heaters. The rest of the heat doesn't go to waste. It helps keep the spacecraft warm. Engineers also wrapped Voyager in carefully designed thermal insulation, allowing it to retain as much of that precious heat as possible. Over the decades, as the RTG has slowly produced less power, NASA has carefully shut down non-essential instruments and heaters to conserve every remaining watt. Every decision has been a balancing act. Which systems are most important? Which heater can be turned off without risking permanent damage? How do you keep a spacecraft alive when its energy supply slowly decreases every single year? These careful choices are the reason Voyager continues its remarkable journey today. It hasn't survived because space isn't cold. It has survived because NASA designed it to carry its own warmth into the darkness. An engineering masterpiece that has outlived almost every expectation ever placed upon it. Keeping Voyager warm is only half the battle. The other half is something that sounds almost impossible. Communicating with a spacecraft that is more than 24 billion kilometers away. Every time Voyager sends a message, it travels at the speed of light. That sounds incredibly fast, yet even light needs almost an entire day to cross the enormous distance between Voyager and Earth. Likewise, every command NASA sends takes nearly another full day to arrive. A simple instruction and its confirmation can require almost 2 days. Imagine trying to repair a computer when every mouse click takes an entire day to register. That's the challenge NASA engineers face every time they communicate with Voyager. To make this possible, NASA relies on the Deep Space Network, or DS-1. This global system of massive radio antennas stretches across California, Spain, and Australia. Positioned roughly 120 degrees apart around the Earth, These giant dishes ensure that as our planet rotates, at least one antenna is always able to maintain contact with Voyager. Even then, receiving Voyager's signal is incredibly difficult. By the time its radio transmission reaches Earth, it is unimaginably weak, far weaker than the energy needed to power a digital watch. Engineers must separate this faint whisper from the constant background noise of the universe, using some of the most sensitive radio receivers ever built. Yet perhaps the most astonishing part isn't the distance, it's the technology. Voyager's computers were designed in the early 1970s. They have less memory than a modern digital greeting card, and processing power that is insignificant by today's standards. Despite that, NASA engineers continue to develop new software, test it on Earth, and upload it across billions of kilometers to keep the spacecraft operating. In recent years, they've even revived backup thrusters that had been inactive for decades and recovered from unexpected computer glitches that many believed would end the mission. These achievements aren't miracles. They're the result of decades of experience, patience, and remarkable engineering. Every signal Voyager sends is more than just scientific data. It's proof that nearly 50 years after launch, humanity is still reaching across interstellar space and touching one of its greatest creations. If you enjoyed this journey beyond the edge of our solar system, don't forget to subscribe to SciTech Signal for more cinematic documentaries, exploring the biggest mysteries of space, science, and the universe.